hopefully you guys can tell I am not Dr. Lehman, but we're going to have a good lecture, and we're going to be talking about mixture models today. How many of you guys have heard about mixture models? One, two, couple? Cool. So the goal today is we're going to introduce mixture models, then we're going to say why they're important and why we want to learn about them, and then we're going to get into inference. This inference part is where we're going to connect from last class, and this is going to be all Gibbs sampling. Okay? So we're going to connect a little bit of last class, and we're going to show some new material. All right? So what is a mixture model? Let's say we have data, xi, where I is going to go from 1 to n. What we're going to have here is c. I'll do my notation in a second. Okay, so this might look a little daunting, but it's not. What we're going to have is we're going to have data that's going to come from this sampling distribution. What this sampling distribution is, it's going to be the sum, where these guys are going to be some weight, and this is going to be some density. So think about right now what we've only been working on is just a normal model. So in our case thus far, pretty much we're just going to have one C. C is going to represent the number of, oh sweet, groups or clusters or components. Whatever you want to call it, it's that. In literature, you're going to get a bunch of different words, and you're going to be like, it's the same thing. But think of it as different components. And so right now what we've worked with is this pi would be 1. It's going to be the probability you sample from something. And this is a normal. So what would we be seeing in our data thus far would be just that. We've all seen that. Where this would be our distribution, and we'd call that a normal with some theta values. Okay? What we're going to be doing now is we're going to make this more complex. Now we're going to say we have two groups. So C is going to be equal to 2. We're going to have group 1, and we're going to have group 2. I'm making it pretty obvious here, okay? So this would be group 1, and it's going to come from some sampling, some thetas. Then we're going to have group 2. It's going to come from a different sampling. And what we're going to do, let's just think about how we're going to generate data. We're going to take a coin, two-sided, simple. We're going to flip it with some probability pi 1 to sample from group 1. Then we're going to sample from group 2 with some other pi. Following so far? We all good? Okay? So we have a constraint. Since these guys right here are the probability we're sampling something, we need these pi's to sum to 1. Okay? So for me, the best way to really understand all these parameters is just to simulate data. So we're going to do that in 1 second. I want to talk about this guy right here. Ooh, gotta get better at writing chalkboard. This F. This F can be normals. So normally if you Google and you look up a Gaussian mixture model, it's going to be a mixture of a bunch of normals. It could be gammas. It could be Poissons. Shoot, it could be a normal with a Cauchy. It could be a Cauchy with a normal. It could, those two are the same thing, so disregard that. But maybe you have a normal, and a Cauchy, and a gamma. What you're trying to do with a mixture model is represent your whole population. But let's think about this. If we just take text population, are we all the same? Are we all the same?
No.
No, we're not all the same. We have little brackets and subpopulations. So what a mixture model is trying to do is it's going to be a probabilistic model that helps us categorize all these subpopulations in our overall population. Okay? And so back way when back, like, you know, those older people back, what they used to do is they used to, if they did have maybe a mixture, they would maybe average over, and they would only care about the average population. Maybe this is good for certain, like maybe government only cares about what the average population's doing. But I have a question for you. Let's say we're talking about medicine, and I want to give you guys a treatment, but I'm going to treat you all average, just like the average population. Would you like that? No. So mixture models is going to give us a way so that we can represent these different populations, and we can get specialized treatment for people that are like me, or people that are like you, or you. Does that make sense on why we want to use these mixture models? So let's just simulate data, because simulations hopefully will help clear things up. Okay, so I wrote some code. Is my code fast? No, that's not my specialty. Does my code work? Yes, it does. So what we have here, thank you, Annie, we're going to sample, we're going to have n. This n is going to represent the number of observations we have. So we're going to go into tech, and we're going to sample 200 people. Okay, we're going to keep everything one-dimensional, so maybe heights.
Can you make the text a little bigger?
Oh yeah, someone's home. Enter full screen. That doesn't. It's a good question. Can I just start with this? Yeah. Go maybe system preferences. No, that doesn't work. Preferences. Font. Jack that up. Does that make sense?
Yeah.
Can you see that?
Thank you.
Better? Awesome. Sweet. So we're going to have n, which is going to be the number of samples or people we're going to go get. Then our dimensionality, we're going to keep it to dimensionality of 1. Maybe next time, if you guys want, we can maybe go to 2 or 3 dimensions just to see how things work. But 1 dimension is easy to see. And then we're just going to start off with 2 clusters. Okay? In each cluster, we're going to flip that coin, and you're going to have the same probability of landing in each cluster, or component, or group. I'm also going to have mu as 5 right now, and my 2 sigmas are going to be 1 and 5. So let's just see what this kind of gets us. I should just run. Here's my editor. Run section. Things are going to pop up. Okay. Well, we know, I'll explain this purple graph in a second. We know that there's 2 clusters, right? We know there's going to be this orange one at mean 0 with sigma squared 1. And we know this blue one is at 5 with variance 5. Okay? But we don't get to see this. What's going to happen in real life is we're going to see something like this. So between these 2 plots, when we know the clusters, and we know which ones they're assigned to, it makes perfect sense. But we don't always get to see that. Okay? So I'm going to play with these parameters, and we're just going to talk about what the parameters do, and then we're going to talk about how we're going to estimate these parameters. Okay? So, let's try just jacking up our samples. And what we're going to do is we're going to change the probability of sampling from the first cluster, which means we have to change this probability because they have to sum up to 1. So let's just look at this. Right here, can you tell that there's 2 different clusters? Maybe. You can kind of see a peak here and a peak here. Let's look at what the real data looks like. So what we can see here is that we're sampling less from the first component, or the orange, and we're sampling more from that second component. So our pi value, this bad boy, is representing how much we believe our bigger population is. So if it's male and female in Virginia Tech, you've probably seen, 50-50. But maybe our populations are athletes and non-athletes. We have a bigger population of non-athletes compared to athletes. Does that make sense? So pi is just kind of telling us how much we're going to sample from each group. Our mu's, we're going to make this bad boy 10. And we'll bring this variance down, just to 1. So the variance is all the same. This mu, this might, oh, don't want to run that. Gonna ruin all the good stuff. Okay? So what the mu's are doing, I know you guys probably know this, but let's just make sure we're all on the same page. The mu's are just moving the normal distributions, all right? The sigmas, as we can hopefully deduce, as we all know what normals are. Here, this one up. Let's make this bad boy really big. Just making them distributions. So what we're going to end up doing is, in our Gibbs sampler, is we're going to try and take all these observations, these 2,000 now, and we're going to be like, you're in cluster 1, you're in cluster 2, and we're going to try and put a probability on what cluster it's going to be part of. Does that make sense? Does the sampling mechanism for a mixture model make sense?
I just have a question.
Yes.
So how would you make those two distributions further from each other? What parameter would you twist?
So that's a good question. It's going to be the mu. So let's look at this mu parameter right here. So right now, we're going to put the variances back to 1, okay? Right here is mu. This 0 is going to represent the first group. So we're saying the first group is going to be centered at 0. And that one's going to say where the second group is. So we're going to say it's 10. So if we run this,
Yeah.
first group's at 0, second group's at 10.
But it also depends on the variance because it depends on how.
So the variance,
Yeah.
all great questions. The variance, what it's doing, is saying how spread out those points are.
I mean, if they're spread out more, then they would lie on top of each other.
Exactly.
That's what I mean.
Yes. So variance is going to, but here you go. What I can also do is the variances are the same here. So first group has a variance of 1, second group has a variance of 1. This is unrealistic to have them both at the same in the same distribution, but they're on top of each other now. This is totally unrealistic if we know that we're 0, 1 for both. We'd use one model. So this would be a bad model assumption, but having mu change, because you could even have 2 there and make this even smaller. I don't know what this is going to do, but boom. So it's all about where the means are and where the variances are, if they're going to overlap. Okay? And that's, as you guys can probably all assume, when distributions overlap, it's going to be harder to assign them to a certain cluster. Okay? So let's talk about inference. So, in class Wednesday, we talked about this right here, Gibbs sampling. I'm going to erase this constriction. We talked about Gibbs sampling. Do you guys remember what Gibbs sampling is? Roughly a little bit? Okay. So what Gibbs sampling is it's an iterative method based on the full conditionals. What do I mean by that? It's Halloween time. I needed a ghost to show up. Didn't you get that? It's because of the chalk sweat. Don't judge my spelling. It's a bad thing. Okay, so what we're going to have is we're going to have 4. We're going to have t, where this t is the number of iterations. And so this is when Dr. Lehman was talking about trace plots. We got all the computational power we need right now. This is a low dimensional problem, so just crank this bad boy up and wait for those trace plots to converge. So, big. When dimensionality starts to increase and you start getting more numbers, and your numbers are your sample size is less, you're probably going to need more iterations. Okay? So what we have here, we're going to have a theta 1. In this case, we could have mu. Conditioned on our data. Let me preface this. Back to our example. On Wednesday, where our xi's, normal, mu, sigma squared, or whatever phi, whichever one makes you happy. Okay? In this, we're going to have mu fixed. We're going to have our xi's, and then we're going to condition on our phi. What distribution would this be if our prior for mu proportional to 1 and our prior on phi proportional to phi inverse? What is this?
Normal.
Okay. Normal with what parameters?
X bar.
And?
Sigma squared over n.
Good. Awesome. Thank you, Annie. Okay? So, should be the previous one. Then, what we're going to do, our theta 2, or in this case, our phi, it's going to be a gamma with what parameters?
N over 2.
And? I'm going to hide it, but you guys, what is it? Boom. Okay? If this doesn't make sense, and you still need a little bit more help with making these conditional distributions, Dr. Lehman's going to have a review session Wednesday and Thursday. Okay? So if this doesn't make sense on where these came from, I highly recommend going to the review session because this will show up on your test 100%. Okay? And then N. Additionally, since we need to have a starting location, we need to have phi of 0 because I'm starting with phi t. Does this make sense? So what's going to happen at our first iteration, we're going to condition on phi 0, and we're going to sample. Then we're going to condition on our new mu, and we're going to sample. Okay? Add a little bit of notation so everything's clear. That's a T. Does this look familiar from last class? We all good on the sampling? Okay, we're going to use these exact same properties, but now what we have to do, we have this extra element over here of our clusters. C of N. So C of N represents the C, that makes sense, C, BB, and observation cluster. Assignment. Take that in for a second. So CI is just representing what cluster we think it's going to be in, or the cluster it's assigned to. Everyone good? Okay, so the question is how do we get this chunk, how do we estimate this idea into the Gibbs sampling? Okay? I'm going to draw you an example.
Could there be sigma squared to t minus 1?
Where are you at?
The normal distribution.
Sigma squared?
A normal distribution of x bar. X bar. Yeah, and there should be sigma squared t minus 1. Right? we need to initialize sigma squared in order for
Ah,
it to
yeah, you're
start.
at, yes. Absolutely right. I thought you were saying divided. My bad. Absolutely right. Notation, Lehman is right. Notation while you're standing in front of the class. Hard to remember sometimes. So I want to draw this picture for you guys. What we're going to have, hopefully this will help us, give us some intuition even into our Gibbs sampler. This is going to be our first distribution. Oh, not a cube. Theta 1. Let's just say we're working with mu's, okay? Or one parameter. Now let's go theta 2, okay? I want you to remember, with Gibbs sampling, we're making full conditionals. So with mu, we have mu, and we're going to condition on everything else. So the idea for clustering and trying to figure out this is that if we're given mu1 and mu2, and I tell you, that's my data point. What group do you think it's part of?
1.
1. Fair. What about, say, that's our point?
2.
Group 2. What about that one?
Either one.
It's a little harder, right? Okay. We can even make this a little bit more interesting by having these tails. Let's say we have, let's show them the picture. Here, the clusters are pretty separate. So yes, in this chunk, be a little guessing. But we could also have distributions. That's 1. And that's 2. And here's our x point. Okay? But the key here is that given all of our parameters, what is the probability that that point is in that cluster? So let me see if I can, let's write that out. Probability that x of I is in cluster C given our parameters. We'll extend this to that problem in a second. Does anyone see where we could potentially, we're going to end up, rephrase that. So given the parameters, you guys can probably figure out probabilistically where x1, x2, x3 would live, right? Okay? We're going to use this here. So now when we sample through mu, we sample through phi. Now we're going to have to do this. Okay? So what's going to happen? We're going to also have to find the probability that x is in the clusters given our theta 1t and our theta 2t. Okay? Everyone good so far? Any questions? Okay.
In this case, theta 2, does it represent the mu of the second cluster?
So it can represent, good question. Right now, think of it more general where this theta could that's a really good question. Bad notation. So what this theta could represent, what we're going to do is we're going to mix this up. How do I want to do this? C's. We're going to add C's here. Actually, just pretend you didn't see any of that. We're going to rewrite it. Yep. Because what's going to happen is we're going to, I see what you're saying. Let's back this up, back it up. Probability that this x is going to be part of C. Conditioned on, in our original mixture model, U1, sigma squared, oh, I don't like that, we're going to use Okay? So in our mixture model content, we have for each of the clusters, our mu's and our p's. Then what we're going to have to do, f of mu c, c is going to represent our cluster, conditioned on our data, and then phi 1 of t minus 1. I'm going to do something kind of weird, but I'm going to explain it in a second. Okay, so, and then our C's. I have a question. If we are given the community assignment, so we're saying C1 and X3 are in the first distribution. It's in the first group. So we know that these points over here are in group 1. You know the cluster assignments. What would you do to try and estimate the distribution parameters?
Estimate them separately.
Estimate them separately. So we know that these points over here, when we sampled them, we ran this. Haven't shown you how to do that yet. We ran this, and we're like, these guys are in this mixture. Then what we're going to do is we're going to run that Gibbs sampling algorithm over just those points in that first cluster. Does that make sense? So given the community assignments, how are we going to find the mean and the variance? We're going to only use the community, we're going to only use the observations from that community. So we know the community assignments, and we're trying to estimate mu c. We would probably only need the respective c. We don't need that mu. Okay, so if we're trying to estimate mu1, we will only probably use this phi 1. Yes, Annie?
Are you saying that when you, by that probability statement, you're going to find whichever probability is higher and do that assignment?
So
Like
what's going to
strict
happen
assignment?
is we're going to end up using Bayes' rule. Because remember, we have priors on mu and we have priors on phi. We need a prior on the probability that we would sample. So a priori, what do we believe our chance of getting into the two mixtures, one of the two mixtures is? So what I haven't told yet is that we're also going to have a prior on C. For simplicity, we're just going to go 1 over the number of clusters. So a priori, we believe that each cluster is equally weighted. Okay? So what's going to end up happening is to compute this, is we're going to do a little bit of Bayes' theorem. And we're going to get a probability of being in group 1, and a probability of being in group 2. And we're going to flip a coin. If the probability of 1's higher, you're going to be in that. But if you get into this case right here, and it's kind of in the middle, you should expect the probabilities to be almost the same. When you flip a coin, it's kind of going to be bouncing back and forth until it figures it out. Does that make sense, Annie? Yes.
Also, the number of clusters should be initialized for the algorithm, the total number of clusters.
The total number of clusters. Yes. So right now we're assuming we know the number of clusters. So algorithms like k-means or EM, you also have to put in a number of clusters ahead of time. There's other processes, such as Dirichlet processes, which kind of do more of an infinite mixture model, but right now, let's just focus on finite. So yes, we're kind of assuming we know what the number of clusters is. There are a lot of parametric techniques that you could do of, let's do 2 clusters, 3 clusters, 4 clusters, and then compare the models using quantitative metrics. But let's not worry about that right now. Is that okay? Does that answer your question as well? Fantastic. Okay. Where was I at?
The steps.
Thank you, Anne. Okay, so we're going to sample cluster assignments. We're going to then compute the mu for each group. And then we can't forget about little loci. Let me add all my indices because mu1 or mu2, it depends on which one, of course. And then our C's. We'll go C then. that make sense? Any questions about the idea? So what's going to happen is we're just going to keep iterating through these.
The first step is basically finding pi, right?
So the first step, you're going to end up finding the probability for each xi and what it is in each cluster. So let me write this part out, and then we'll simulate, we'll show some trace plots and get some idea.
But isn't that the probability by C?
So the question, so you guys are asking what this is doing. It's a fantastic question. What it's going to end up doing is I'm going to use theta 1 to represent mu1 and phi1. Simpler notation, you guys are okay with that. Condition on C. Then we're going to have our prior. All I'm invoking is Bayes' theorem. That's C. Okay, so what's happening is, given we're in a cluster and X, so here's an X. I'm going to say, given all of our parameters, what's the probability we're going to be in group 1? Okay, with our a priori. Now, what's the probability that this same point is in cluster 2? We're going to end up taking those two numbers and dividing by the sum of them. Okay? This is normalizing constant. All this is doing right here is Bayes' theorem. And invoking that. So what's going to end up happening, how I view it, is for each x1, I'm going to get a probability that it's in cluster 1, probability it's in cluster 2. If it's like this x1, it's going to have a higher probability of being in this cluster. Okay? And so what's going to happen, you get those two probabilities, you're going to flip a coin. We're probabilistic, we're Bayesians. It's going to have a really good chance of being in group 1 compared to group 2. Same thing with x2. The question is when it lies here. And it wants to be a tricky person. So we're not really sure, so those probabilities will probably be the same. And it's that point will end up kind of bouncing around a little bit in your thing. But as cool as it is for me to talk about this, I think sims and seeing convergence and trace plots might help you guys. At least that's what I'm hoping for. So let's just, yes.
So what is the C here? Is it something like
This C?
there's a specific assignment of cluster?
Yes.
So it's like
So our
it's
C,
like CI, so in I cluster.
yeah, so this C, big C, this right here is going to represent our a priori belief, which we're going to say is just 1 over the total number of clusters.
Okay.
Okay? Cn is representing that this nth observation is assigned. So if I said, let's look at this x1, then C of 1 would be in group 1. C of 2, is our second one, would be in group 2. Does that make sense? Can I clarify? Dan?
So when you go to sample now, after these two draws, when you go to sample from, say, to estimate the variance of the first distribution there, you only condition on C1, right?
Correct.
Okay.
Exactly. So it might not be too clear in this, but since we're given those cluster assignments, would we want to use cluster 2 observation to help us estimate cluster 1?
Yeah, probably not. I just-
Yeah. Yeah. So this is a great question. Yes, Anne?
I think you're thinking the C would be like a vector of length n. Is that correct?
C,
Because for each
yeah,
I,
so this Cn would be the size of n.
it would be like a whole vector.
It would be a whole vector. So how I see it is when I'm computing this step in my code, that's an I. Computing this, I'm thinking, all right, I'm gonna have a matrix of n, and then I'm gonna have the probabilities that it's in each cluster. That's how I view it. Other people see different things, but that's how I kind of see it. So, yes, absolutely.
So in the first step, we calculate the probability of each xi in each cluster.
Yes.
So, but I don't see how this step used in the following steps.
Okay.
Or the first step used.
That's fantastic question, fantastic question. So what we're doing here is we have this xi, and we're going to say, we're going to find the probabilities that it's in cluster 1 and cluster 2. We're going to flip a coin and say, okay, it's in cluster 1. So for the rest of these two steps, that x1 is in cluster 1. And so we're going to do that. We're going to do that for each xi. Okay? So after this step right here, each of our xi's are categorized into their clusters. Okay? Now, if I said, here's your data, this is cluster 1, what would you do to estimate those parameters? You'd probably only use that data, rather than the ones that we said were clustered with cluster 2. Does that make sense?
So in the first step, the condition x is the axis, the x that's in the certain group, the certain cluster, right?
Yes.
The second step.
So what, this step?
Yeah, so the x.
Yeah, I see what you're saying. So these would be the x's that are in cluster C. So notation's a little bit wonky, but here's the x's, and then I'm also giving you the assignments for each of those x's. Does that help clarify a little bit? Okay. Notation's a hard thing, you guys. I don't know how people write it. We'll go with Dan first.
So just, do you recluster at every step the previous n-1 observation, or t-1?
Yeah,
whatever it is? Okay.
so what's gonna happen is, we now get our mu's and we now get our phi's, so let's re-update what we think our x's are.
Thank you.
And so it's gonna be through this iterative process. Do you have a question?
Yeah, if I'm understanding correctly, so in the first step,
Yep.
we are just calculate the probability that's assigned to each cluster, and
Yes.
we assign it to the highest probability.
So it's not, it's a good question. This is something that I was confused about when I was first learning this, is we create these probabilities. It's not, okay, this one's 0.98 and this one's, whatever makes it 1, 0.02. Oh, this is higher, we can assign it to that.
Yeah.
It's, we get those probabilities, then we're gonna do a coin flip, because it's a
Okay.
probabilistic model.
Okay.
Does that make sense?
So we flip the coin based on the probability.
Based on the
distribution.
probabilities of which one we
Okay.
think it's gonna be in.
Okay.
Because if it's, imagine we have this point, it's 50-50.
Yeah.
Neither one's higher, so we need that probabilistic part in there and helps it. Does that make sense?
Yeah, thank you.
Awesome. Oh, might need this. Okay, so our Gibbs sampler, because we have this extra element, and imagine every time we do an iteration, we have to calculate this part n times. So I'm going to drop down our sample size, and this will look good. So we're going to sample data. Sample data, this is what our data is going to, let's do it better something. One. Sample data. And make it a little bit further, and then we'll make things hard. Make life really easy in the first. Even our eyes can tell us probably what cluster, right? So I'm setting the seeds for something else. Run this section. It's gonna take a little bit. I'm running my Gibbs for 500 iterations. Reason why it's relatively low compared to most other Gibbs samplers is we're in one dimension, and this problem is relatively easy. So if I pull this up, that's my initialization. So what I'm doing, I'm not going to show you all the code, but this code right here, make it go to something else. I'm sampling my C's. Okay? Code's not the cleanest, but I'm gonna sample some C's. Then, given those C's and given that data, I'm gonna sample my Mu's. Oh, cool, picture came up. Boom. So right here is mu1, and we had 0. Do you guys agree that that is pretty stationary, caterpillar-ish, around 0? This guy up here, 5. You guys agree with that? Down here, we have 1 and 1. So our groups were pretty separate. Other methods could probably do the same. Okay? Let's see. What else do we want to try? Do we want to try the Mu's closer, maybe?
Yeah.
Okay. Let's try it. So run, get some data. It's kind of what we'd be seeing. Might be a little hard. Let's see what our Gibbs sampler does. Again, I'm only running it for 500 iterations, more because we're in class, but we could also always run it for longer. Yes?
What's the step we are learning pi?
What step? Oh, the
Yeah, the weights. Yeah.
so we're essentially learning the pi's for each xi. And let me try and think of how I want to say this properly. Oh, should I picture too? Oh, hit the table, it works. So, again, our trace plots aren't the look super good and super tight, but we're running it for 500 iterations. And to my eye, we're already converging here at 0. It's a little bumpy. Run it a little longer, it will smooth out. And this guy's around 3. This guy's around 1 and 1. Does that make sense? So your pi I is what? Yeah, you're not necessarily calculating the pi's as a big. It's more for each observation. Does that make sense? It's a good question. I'm not exactly sure.
I mean, the C vector converges to pi, doesn't it? At the end?
Yes, it would be. So you could take your CNs and be like, I have.
Yes, I'm
What's that?
thinking you might be able to take your x vector at the end that you have like the final components and just take a proportion. Like I
Yeah,
have 20% in
yeah.
component 1, so
I'm
20.
trying to do that currently. We'll see if it works. Errors, love them. Which oh, it's a character. Okay, how about next time? How I end up doing the label assignments, I make them a character, not a number. And I'm gonna be real honest with you guys, my coding skills aren't that fast to fix this real quickly. But I can fix it, not under pressure. But what we can also do, just give you guys another example before we leave. I do have something a little bit different compared to Dr. Lehman. Since this is my first time teaching a graduate level class, I kind of want to do something to get y'all's feedback of what made sense and what didn't. So I'm going to pass out some papers, and pretty much what I want you to do is write down what you found confusing and what you might want some more clarification on. This is to help me so that on Monday I can better help you guys. Okay, there are no wrong answers. Clarify that, there are no wrong answers. And so while you guys are doing that, we're gonna run another sim. And then, again, so whatever you found confusing, what you want me to elaborate on, this is gonna help me become a better teacher and it's gonna help me make a better lecture and help you guys out next time. Let's go.
So, what's the final objective of this?
The final objective, so imagine you have this data. As an experimenter, I give you this data and I'm like, I want to know the parameters. I can tell you there's 2 clusters of people or populations, but I want to know what's kind of telling us about this. So the goal of this is to be able to estimate the mu's and the sigmas for each of those clusters so that if we're in a medical treatment, I'm not treating you as an average. I'm treating you as your subpopulation. And I'm not treating Melissa as average. Or anyone else like that. Does that make sense?
But why do we want a mixture model instead of like a joint two?
Ah. So your question is why not just have one model?
No, why not the joint distribution instead of mixture model?
Yeah. So instead of adding those f together, we multiply them together. Joint distribution.
So then, let me think about it. You want to be treating them as different, I believe. That would be my first answer. Let me get back to that on that. Because if I said, here's the male population density and here's the female, let's just multiply them together, that really wouldn't be getting at what we want to try and do, which is say, here's what the females are doing and here's what the males are doing. You're ending up like mixing. You're not, ooh, mixing is a really bad word for mixture models because we're not doing mixture models.
There's the possibility that there is a thing that both female and male would do. So we want the joint.
So you'd want to be, how about this? Let me get back to you on that question. In my head, let me get back to you on that. Because in my head it makes sense, but I'm not getting it out properly, and we'll get to that one. Does that sound good? So, I'll show you the trace plots. We'll see how they look. Trace plots. So, doesn't look like that. Oh, because I didn't run the Gibbs Sampler. In order for your code to work, you have to run it, I've realized. It's a very thing. This outputting, I'm a very impatient person. I like to know where my code is at, so that's running. Are there any other questions that I could potentially clear up? Dr. Lehman will, oh,
Okay, so just picking on your notation and,
Yes.
So on the probability of X belong to some cluster,
yes.
like on the numerator, so the theta 1 and theta 2 are are from the last iterations. Like those are, so you're using the points that you sample
Yes,
from
yeah, so
the last
these,
one.
is this what you're saying, that these should
Yeah,
have
so
the
they
T?
should have the T,
Yes,
yeah.
absolutely. Maybe next class I work on my notation, just come back, re-clean it up, will be one thing definitely. So this looks like it's working. I don't remember what our parameters were, but things are converging. Does that make sense?
Can we see the picture again?
Where'd the picture go? All right, lost the picture. But this would be what it somewhat looks like.
That's interesting, because it looks like it really nails the mean, but not the variance of those. So I can't see why that would be.
Variance was, yeah, fascinating.
Or no,
It
I
gets
see,
more
Is
about
I
this
see,
one-
right, yeah, I see. The other one, the one it sampled way more from,
Yeah,
they got it, I see.
so if you don't, so this bad boy right here, we were sampling a lot less. So
Right.
imagine you have a lot less data and you're still trying to figure out that variance. It's gonna be a little bit harder. So if we ran it longer, we had more time, we could do that, and I would bet you it would converge eventually. Does that make sense? I hope you guys all have a really good weekend. I'll take those papers back so I can figure out what I can work on. And on Monday, we're gonna do mixture models again. Wednesday and Thursday, we will have a review session. Have a good day.
Bye.
See you later.